Hello everyone, welcome to the Magnificence of Mathematics. I'm your host, Eddie Kingston. Last time we touched on a simple yet beautiful geometry problem from Paul Lockhart's A Mathematician's Lament. You may remember geometry from your high school days as finding areas and volumes and working a lot with triangles and circles and whatnot. But what if I told you the rules of geometry as you know them behave differently on different surfaces? Today we'll be diving deep into the history of the geometry you know and love or hate, talking about Pythagoras and Euclid, and finishing off with what's known as non-Euclidean geometry. Now, most of you listeners have probably at least heard of the Pythagorean theorem, a squared plus b squared equals c squared. Here's what this means so that you can try to visualize it. Take the length of one side of a right triangle, either the horizontal or the vertical side, and multiply it by itself. Take the length of the other side, whichever of the horizontal and vertical side wasn't used before, and add them together. That is equal to the length of the hypotenuse, the diagonal side, multiplied by itself. But where did that come from? Well, it might surprise you to know that it wasn't even Pythagoras who discovered this theorem. It was first discovered by the Babylonians in Mesopotamia, which is modern-day Iraq, Syria, Turkey, and Kuwait, between roughly 2000 and 1800 BCE, together with other known math at the time for certain crafts in astronomy. Nowadays, it's used for things like architecture, painting, engineering, navigation, forestry, etc. Fun fact, did you know that there's over 370 proofs of the Pythagorean theorem? That's over 370 different ways to demonstrate why the theorem is true. Some of these proofs were written by 12-year-old Albert Einstein, Leonardo da Vinci, former US President James Garfield, and of course Pythagoras and his students. The most recent of these proofs was discovered in April 2023 by two high school students from New Orleans, Louisiana, Kelsey Johnson and Nakia Jackson. That's something that I really like about math. There's so many ways to solve a problem, and there's new proofs still coming out from problems that were posed millennia ago. A couple centuries after Pythagoras' time, Euclid came along and revolutionized geometry, inspiring mathematicians over the next couple thousand years to study his work. In about 300 BCE, he wrote his magnum opus, The Elements, a collection of 13 books spanning 2D and 3D geometry, as well as elementary number theory. In the first book, Euclid described 5 postulates, from which the rest of his work follows, although some scholars disagree that everything follows from just these 5 axioms. There's probably more that are needed. These axioms, at least the first 4, might seem pretty straightforward. First, given any 2 points on a 2D plane, you can draw a line connecting those 2 points. Second, you can extend that line to go on forever. Third, you can describe any circle given its center and radius. Fourth, all right angles are equal to each other. 90 degrees is 90 degrees. The fifth postulate, called the parallel postulate, is rather infamous. Take a straight line and a point not on that line. Then there is exactly one line going through that point, such that the 2 lines never touch each other, even when those lines are extended infinitely. People tried proving the parallel postulate for quite a while, but then it was discovered that by tweaking it a bit, or abandoning it altogether, one could describe entirely different, yet still valid systems of geometry that behave differently from Euclidean geometry. You know the angles on the triangles that you're used to add up to 180 degrees, but did you know that there's surfaces on which the angles of a triangle add up to more than 180 degrees, and some on which the angles add up to less than 180 degrees? This is where various Riemannian geometries, such as hyperbolic and elliptic geometry, come into play. The underlying feature here is the idea of curvature. An intuitive way to think of curvature of a space is that it's a measure of how much space opens up or closes in on you as you move across it. In Euclidean geometry, space is completely flat, that is, there's no curvature involved. If you walk across a flat surface, it'll continue to appear flat for you. For hyperbolic geometry, pretend you're standing on a giant horse saddle or a giant Pringles chip. If you walk across this surface, you'll notice the surface appearing to open up away from you. This is what's known as negative curvature. For elliptic geometry, pretend you're standing on a ball or sphere. If you walk across this surface, it'll appear as though the space is bending towards you or closing in on you. This is an example of positive curvature. Curvature in this sense was first quantified by Bernhard Riemann in the mid-1800s via what's known as a curvature tensor, which ends up being quite complicated when you get into the nitty-gritty, which I won't do here. Riemannian geometries are kind of like Euclidean geometry, but without the parallel postulate. Let's say we have a line and a point not on the line. In hyperbolic geometry, there are an infinite number of lines going through the point that don't intersect the original line, whereas in elliptic geometry, any line through the point intersects the original line, so there's no parallel lines in elliptic geometry. So in hyperbolic geometry, you end up with triangles that are strictly less than 180 degrees. Meanwhile, in elliptic geometry, you end up with triangles that are strictly greater than 180 degrees. For example, say you're on a sphere in one location and start walking before taking a turn 90 degrees to the right. Let's say you walk the same distance as before and take another 90-degree turn to the right and walk the same distance that you have before. You actually end up back where you started, but the angles in the triangle you just walked in add up to 270 degrees, 90 degrees for each side, instead of the 180 degrees with 60 degrees on each side that you'd walk if you were in flat space. If you were to try walking on a hyperbolic surface, you would need to turn somewhat less than 60 degrees each time to end up back where you started. If you'd like a visualization of walking in hyperbolic space, I highly recommend checking out the game Hyperbolica by Code Parade on Steam, or at least watching gameplay videos of it on YouTube. I personally haven't played it yet, but I think this is a great complement to what I've been describing here. Thank you for tuning in to another episode of the Magnificence of Mathematics. Next time I'll talk about my personal favorite math subfield, probability. See you then!